Welcome to module 2 of lecture 6. In the last module, we had started with allocation and binding, an important post scheduling step in high level synthesis. In this lecture, we will proceed with allocation and binding further. Before taking a look at allocation and binding algorithms, we will first take a look at different resource sharing models. We will look at a few definitions. First, we will understand what are compatible operations. Two operations are compatible if they can be bound to the same instance of a resource of given type. That means, when does two operations become compatible? When the same functional unit can be used to execute both these operations. When can the same functional unit instance be used? When the two operations are non-concurrent. If they are executing at two different time steps, only then can I use the same functional unit to execute both these operations on the same functional unit. And obviously, they have to be implementable by resources of the same type. Now, with the definition of compatibility, we will take a look at two types of resource sharing graphs. So, first is the resource compatibility graph, the other will be resource conflict graph. These two resource sharing graphs we will understand. So, what is a resource compatibility graph? In the resource compatibility graph, the vertex set are operations. There is an edge between two operations if these two operations are compatible, which means that there will be an edge between these two operations if both these operations are not scheduled at the same time step and both these operations can be executed by an operator of the same type. A group of mutually compatible operations then form a clique. Here, what is a clique? A clique is a maximal complete subgraph, right. So, a set of mutually compatible operations form a clique or a complete subgraph. Why? Because all these operations will be connected by edges between each other. And why are that so? Because all these operations are mutually compatible. Neither of these operations are scheduled at the same time step, and the same functional unit type can be used to schedule all the operations in this clique. A distinct resource instance can be dedicated to each clique. An optimal solution to the resource sharing problem is what? One that maximizes resource sharing. So, the optimal solution will be one that minimizes the number of resource instances. So, how do we minimize the number of resource instances? If we can minimize the total number of cliques, for each clique I must dedicate a single resource instance, and if we can minimize the total number of cliques, I will be able to minimize the total number of resource instances required. So, partition the graph into a minimum number of cliques, and obtaining this minimum number of cliques is to obtain the clique cover number. So, the clique cover number of a graph is this minimum number of cliques into which the graph can be partitioned into. Now, this is a scheduled operation constraints graph on the left, and on the right we have the corresponding compatibility graph. In this graph, we see that operation 1 and operation 3 share an edge. Why? Because operation 1 and operation 3 can be implemented by the same resource type multiplier, and they are scheduled in different time steps 1 and 2 in this case. Similarly, 1 and 7 are also compatible. Why? Because 1 and 7 are two operations that can be implemented by the same type of functional unit multiplier again, and they have been scheduled in different time steps, here time step 1 and time step 3. Likewise, all operations which share an edge are compatible. One important thing to note here is that the compatibility graph will have as many disconnected components as there are resource types. So, here we have two resource types, multiplier and ALU. So, for ALU I have a single a connected component and another connected component for the multiplier operator type. Now, what are the minimum number of clicks? What is the minimum click partition in this graph? We have here V1, V3, V7, V1, V3, V7. So, the one with emboldened edges. So, these complete subgraphs with emboldened edges form the click. So, V1, V3 and V7 form a click, V6, V8 and V2 form another click, V4, V5, V11 and V10 form another click, and V9 forms another separate click. So, these are the this is the minimum click cover that we have. So, the minimum click cover has 4 clicks, and indeed we require 2 multipliers and 2 ALUs for the scheduled operation constraints graph. Now, as an example of the actual resource binding that we can obtain here is this. So, we have one multiplier, say let us say multiplier 1, multiplied instance 1 is used to schedule operation 137, which is in the same click. Again, another multiplier, say multiplier 2 is used to execute operations 2, 6 and 8 in time steps 1, 2 and 3. Similarly, ALU 1 is used to execute the operations 10, 11, 4 and 5 in 4 different time steps, and operation V9 is given another dedicated ALU for its execution. So, this is an example allocation, and this is the best possible allocation as it turns out. The second resource sharing model is the resource conflict graph. Resource conflict graph has the same vertex set as the compatibility graph. So, its vertex set are also the operations of the operation constraints graph. What are the edges? There is an edge between two operations if they are not compatible. That means, in the compatibility graph, two operations shared an edge if they were compatible. In the conflict graph, two operations share an edge if they are not compatible. Hence, the conflict graph is a complement of the compatibility graph. So, when will two operations be conflicting? When these two operations are scheduled either in the same time step, or these two operations are unrelated, in meaning that they cannot be executed using the same functional unit type. However, it is true that if you have a set of compatible operations, they will form an independent set. What is an independent set? The vertices in an independent set will be those which do not share an edge between them. So, mutually compatible operations will form an independent set. A proper coloring of vertices such that no two adjacent vertices share the same color provides a solution. So, what do the vertex coloring do? Vertex coloring tries to find the minimum number of colors that are required to color the vertices of a graph such that you cannot assign the same color to two vertices that share an edge. These colors actually denote resource instances. Each color is a resource instance. An optimal solution uses the minimum number of colors. Such minimum number of colors is called the chromatic number of the graph. Example of a conflict graph. So, in this we see that 3 and 6 share an edge. 3 and 6 share an edge. Why? Because 3 and 6 are operations of the same type and being scheduled in the same time step. Because they are scheduled in the same time step, they are conflicting and cannot be executed by the same resource instance, and therefore, they share an edge. Obviously, 3 and 4 also share an implicit edge which is not shown, because 3 and 4 are two operations, unrelated operations, which must be executed by operators of different type. There is an implicit edge between them which we have not shown here. Now, what are the independent sets in this conflict graph? 3, 7 and 1 is an independent set, they do not share an edge between them. 2, 6 and 8, 2, 6 and 8 is another independent set, they do not share an edge between them. 4, 10, 5 and 11 is another independent set, and V9 forms another independent set. It is important to note here that the clicks in the compatibility graph are now independent sets in the conflict graph. The chromatic number here is same as the vertex cover number in the compatibility graph is 4, and therefore, we again require 2 multipliers and 2 ALUs. Allocation and binding will again be same. Now, one of the important outcomes of this analysis study of these models is that given general compatibility and conflict graphs, both the minimum click partitioning problem and the minimum graph coloring problem are NP complete, and hence exhaustive and enumerative type solutions only do exist for the general versions of the compatibility and conflict graphs. Now, with this understanding of resource models, we will first we will now see how from the scheduled operation constraints graph can we obtain a compatibility graph. Similarly, we using a similar procedure, we can easily obtain the conflict graph as well, because as we have seen that the conflict graph is just a complement of the compatibility graph. Now, given a scheduled OCG, let n be the number of operations. Resource type of an operation is denoted by tau Vi. This comes from the scheduling problem. So, tau Vi tells me the type of resource that I require to schedule operation Vi. The start time of the operation is Ti, because this is a scheduled operation constraints graph. I know the distinct start time for each operation I. The execution delay of operation Vi is also known, this is Di. So, the compatibility graph will have edges E equals to Vi Vj such that Tvi equals to Tvj. The first term tells me that both Tvi and tau Vi and tau Vj must be same. That means they must Vi and Vj must be executable by the same type of resource. The second constraint tells me that if Tj is scheduled later than Ti, then Tj must be scheduled at least Di time steps later than Ti starts. So, Tj start time must be at least Di time steps after Ti. Why this is so? Because Di is the delay of operation I, operation Vj follows Vi, and hence otherwise there is an overlap in the execution intervals of these two operations, and therefore, the same operation instance cannot be used to execute both these operations Vi and Vj. Similarly, if Vi starts after Vj, then Vi must start at least Dj time steps after Vj starts. So, Tj plus Dj must be less than or equal to Ti. Only then can I ensure that both operations Vi and Vj will not overlap in their execution intervals, and hence both these operations Vi and Vj can be implemented by the same type of resource. Now, we understand that how can we obtain these edges. I need to traverse the operation constraints graph, and then I need to consider each operation in the scheduled operation constraints graph. Then I find out which for a given operation in the operation constraints graph, which are the operations that are adjacent to it in the operation constraints graph. For all those operations, if this constraint is true, I can put an edge between these two operations in the compatibility graph. Now, through such a traversal of the operation constraints graph, we understand that all edges of the compatibility graph can be obtained in big O of n square time, where n is the number of operations in the operation constraints graph. Now, as we said, for general compatibility and for general compatibility and conflict graphs, both the minimum click partitioning problem and the graph coloring problem is NP complete, and hence must be solved by enumerative methodologies. However, there are special classes of graphs for which both the minimum click partitioning problem and the graph coloring problem can be solved optimally in polynomial time. So, if my compatibility graph or my conflict graph falls into one of these categories of these special types of graphs, then my graph coloring problem or my click partitioning problem can be solved optimally in polynomial time. Hence, we need to understand these special types of graphs first to understand whether my graph coloring problem and the click partitioning problem can be solved in polynomial time or not. So, first we understand what are chordal or triangulated graphs. If we say it in terms of a compatibility graph becomes a chordal or triangulated graph when every cycle with more than 3 edges in the graph has a chord or edge joining two non-consecutive edges in the cycle. So, I am given a compatibility graph and I want to find out, is this compatibility graph a chordal graph? How do I find out? If I see that each cycle of more than 3 edges in my compatibility graph has a chord joining non-consecutive edges in the cycle, then I can say that my compatibility graph is a chordal graph. For example, let us take this compatibility graph that I have here. In this compatibility graph, let us take one cycle 1, 3, 7, 6. In this cycle, we say that there is a chord 1, 7 here. This chord, this is a cycle of length more than 2, this is a cycle of length 4, and we have told that every cycle of length more than 3 for every cycle of length more than 3, I will have a chord joining non-consecutive vertices, and hence these vertex 1 and 7 are non-consecutive, and hence there is a chord joining it in this cycle 1, 3, 7, 6. Similarly, we will see that for all other cycles of more than 3 of length more than 3, similarly we will see that for all other cycles of length more than 3, I will have a chord joining non-consecutive vertices in the cycle, and hence this compatibility graph that we have here is a chordal graph. Now, therefore, the minimum click partitioning problem for this chordal graph, for this compatibility graph, can be solved now optimally in polynomial time. After an understanding of chordal graphs, we will now understand what interval graph is. Simply speaking, an interval graph is a graph where the vertices have a one-to-one correspondence with a set of intervals. For example, let us consider the scheduled operation constraints graph here. In this scheduled operation constraints graph, each vertex can be represented by a continuous single interval defining its start of execution and end of execution. So, each vertex or each operation in this operation constraint graph can be represented by a single continuous interval representing its start of execution to the end of its execution. So, Ti to Ti plus Di minus 1, this interval is the interval for vertex I. For each vertex similarly, I can define a continuous interval which denotes the lifetime starting from the start of its execution to the end of its execution. And hence, simply speaking, all the operations in this operation constraints graph have a continuous interval, and hence the corresponding compatibility graph or the conflict graph is basically an interval graph. So, interval graphs are a subclass of chordal graphs. If you have an interval graph, the property for chordal graphs will always be true. So, vertices can be put in one-to-one correspondence with a set of intervals. Vertices are adjacent if corresponding intervals overlap. So, vertices are adjacent if corresponding intervals overlap. So, in my interval graph, vertices are intervals and there are edges between two vertices if their intervals overlap. Now, we come to the third class. So, why have we studied interval graphs? We can still have more simpler algorithms for both clique partitioning and graph coloring for interval graphs. As we will see later, we will study one algorithm for interval graphs, for graph coloring of interval graphs. Now, we will look at the third class of graphs. A graph becomes a comparability graph when it satisfies a transitive orientation property. So therefore, I need to be able to impose a transitive orientation property on my graph. So, my compatibility graph or my conflict graph can only become a comparability graph if I can impose this transitive orientation property on this graph. Now, if I impose a transitive orientation on an undirected graph, it becomes a directed graph. So, my compatibility graph or my conflict graph will be a comparability graph when, after imposing this direction property on the compatibility graph, I will have this. In the resulting directed graph G equals to V comma F, Vi Vj belongs to F and Vj Vk belongs to F implies that Vi Vk belongs to F. So, this direction property, this transitive direction property will be imposable on this graph. As an example, let us see this compatibility graph that we have here. So, in this compatibility graph, we have an edge from 1 to 6 and we have another edge from 6 to 7. So, let us see, this is Vi, this is Vj and this is Vk. So, if I have an orientation, if I impose an orientation from V1 to V6, from Vi to Vj, I have an orientation from Vi to Vj, and then I also impose an orientation between Vj and Vk, I can impose an orientation from V1 to V7. So, if there is an orientation from Vj to Vi to Vj and there is an edge, an oriented edge from Vi to Vj, there is an oriented edge from Vj to Vk, there will also be an oriented edge from Vi to Vk. This is what this ensures, and hence this compatibility graph is a comparability graph, because for all edges I can impose an orientation property like this. Now, on this, how can we get a sense of how to obtain this orientation? We can assign an orientation with respect to the order of start times in the operation constraints graph. Now, here there is we are putting an orientation from 1 to 6 because 6 starts after 1 in the operation constraint graph, 6 starts after 1. There is an orientation from 6 to 7 because 7 starts after 6, and hence there is an edge between 1 to 7 denoting that 7 starts after 1. Such an orientation can be imposed for all edges, and hence this compatibility graph is a comparability graph. But why are we studying these graphs? By studying the chordal graphs and the comparability graphs, we can find out whether a graph is whether the graph is an interval graph or not. If my conflict graph is a chordal graph and the compatibility graph is a comparability graph, then the conflict graph is an interval graph. So, if this conflict graph is a chordal graph, here this conflict graph is a chordal graph because there are no cycles of more than 3. In fact, there are no cycles in this graph, and hence this conflict graph is a chordal graph. We have seen that this compatibility graph is a comparability graph. We have already understood this, and therefore, this conflict graph now becomes an interval graph, right. The general theorem is that a graph is an interval graph only if it is chordal and its complement is compatibility graph. Here we know that the compatibility graph is a complement of the conflict graph, and hence if the conflict graph is chordal, the compatibility graph is a comparability graph, then the conflict graph becomes an interval graph. We come to the end of module 2 of lecture 6.